let's see, here's the recording. I have open your last formative assessment, which I looked through this morning, so we have that to go over. I wanted to give you an update as to how course evaluations are coming along. So let me get that screen share going so you can see where we're at for the class. This group is at 24 out of 26. So two more is what we need to hit the goal of 26, but you are beating the other class. So there is that. I'm going to send out a reminder. You can see I have access to this little reminder button. I don't know who has done it or not, but I can have the system email those who have not, so I will do that tomorrow. So, do you want to do formative assessment 6 first or homework questions first? Any preferences? No? Formative assessment, since I have it up here? FA, yes indeed. So yes, they're quizzes, but they're not really quizzes. All right then, so first question meant to help you transition into analyses in the real world, where you don't necessarily always know everything that you should know about the variables that you're going to be working with. So the question is, when faced with an unfamiliar data set, how can you determine whether a predictor contains level 2 variance, level 1 variance, or some combination? So I had one strategy in mind, and at least one of you gave me an alternative strategy that would also work. Several of you talked about fixed effects and random effects, but I'm talking about just trying to figure out at what level a variable is measured. That's the question. How could you find that out in practice? What do you think? Any ideas? How do I know at what level a given predictor is measured? We got one vote for ICC. Yeah, that sounds pretty good to me. It doesn't matter if it's a predictor or an outcome. You can put it into an empty model and try to estimate its random intercept variance and its residual variance. And if it is a level 2 predictor, yes, a lot of you overthought this question. That is a common thing that happened with this, which is why we're talking about it. If it is a level 2 predictor, meaning it is time invariant, what should happen when you estimate an empty means random intercept model for it and try to compute an intra-class correlation? If it's a level 2 time invariant predictor, what should happen? Will both of the variance components be estimable? No, it'll be an intraclass correlation of 1 or approaching 1. Which variance is likely to blow up and have like a 0 and some dots next to it? If it's a level 2 time invariant predictor, are you going to have that problem with the intercept variance, or are you going to have that problem with the residual variance? If the ICC is 1 or close to it, which variance component has got to be 0 then? Residual. Yes, level 1 residual would be 0, meaning there is no within-person variation if it is a level 2 time invariant predictor. Yeah. You can, if you have the data sorted by person, you can usually open a data set and scan it, but that's not always going to be sufficient, particularly for big data sets in which you can't easily scan all of the rows. So yes, if you have a level 2 variable, that will be diagnosed with it having only random intercept variance and an interclass correlation of 1. The variable that we've been working with for time this semester is an example of the opposite kind. So in data in which you have balanced occasions, meaning everybody's on the same measurement schedule, a variable for time that is purely within persons would have an ICC of what in this strategy? It's purely within. It'd be 0, yeah. And that means which variance component would be estimated to 0 or very close to it. If you have a purely level 1 variable, random intercept, yeah. Now, what if it's both? That is what is most likely to happen. It is only the case that level 1 predictors are going to have only within person variance, probably if they've been manipulated that way. Otherwise, to the extent that you're measuring something repeatedly, it is almost certain that there will be at least some level 2 between person intercept variance in that predictor, as well as level 1 residual variance. And the one thing that I had hoped we could cover this semester, but we're not going to get there. So you'll note that I redid the printable version of the syllabus so that it actually covers what happened in the class as opposed to what I had planned for and missed. And I lumped together all of the stuff that we didn't get to talk about with respect to time varying predictors, and I've posted 2 resources. In the advanced version of my multi-level class that I last taught in 2018 at KU, I have a whole bunch of examples about time varying predictors and other stuff. I also gave a workshop in the before times, as people are calling them now, at Oklahoma State University entirely on this topic. The one thing that I can tell you, just very, very briefly, is that if you have a predictor that has partially between person information in it and partially within person information in it, it goes into the model at both levels. This is the one thing that people screw up so commonly in multi-level modeling still to this day, is to not put in a level 2 representation of a time varying predictor. It is a problem that I refer to as creating a smushed effect. If you only put it in at level 1, then its between person variance and its within person variance are constrained to have the same level of prediction across levels. So for the same reason that we have to be very concerned about levels of variance in a time varying outcome, you have to be equally concerned about levels of variance in a time varying predictor. So just know that if you're dealing with time varying predictors, you can't just stick it in at level 1 like we did with time. That's only valid to do if the time varying predictor has only within person variance. But odds are good that is not going to be true for measured variables. So normally it takes a good month to talk about ways of dealing with that. There are multivariate strategies, there are univariate strategies, there's centering strategies that go within each of those, and it's a fairly complex topic. But I just wanted to put a pin in that if you are reading a research article and you see somebody list the effect of a time varying predictor in a table, and there's nothing about it that corresponds to the person level as a separate predictor, that model is wrong. So unfortunately, I didn't get a chance to say a lot about that this semester, but here are some resources for that idea. So I wanted to set up that idea in your head that a predictor goes into the model at each level at which it contains variability. So as an initial planning stage, you want to make sure that you know which levels of variability are contained in every variable that's part of your analysis, whether it's considered an outcome or a predictor. So any thoughts or questions on number 1 then with respect to that? No. All right. Number 2. So 2 questions in parallel here. How do I assess significance and effect size of number 2 of a main effect of a time predictor, and then the same question for its cross-level interaction. So by main effect, I was talking about having a predictor in the model just by itself, like not part of an interaction with anything, just putting in the slope for the time invariant predictor. So what I was looking for here is to recognize that the role of that fixed effect in the model is to moderate the intercept. So if I put in a time invariant predictor, I am taking the predicted outcome and shifting it up or down as a function of that predictor. Whether or not the slope of the time invariant predictor is conditional at time 0 depends on whether it interacts with time. If it doesn't interact with time, then it's saying that it shifts the y-axis up or down equally across occasions. It's like a parallel change. Whereas if it interacts with time, then it would be a different effect of that predictor at each subsequent occasion. so it shifts the y-axis differently depending on which occasion it is. But either way, the role of a main effect of a level 2 predictor is to capture intercept variance. And so the most direct way to describe its effect size would be some kind of R-square for the intercept, either a pseudo R-square relative to a model with no predictors of the intercept, or the model implied version of R-square that Reitz and Sturba have. There's a few other variants, but the same idea is that it should affect the intercept. And so talking about what it does to the intercept variance specifically is the most direct way to talk about effect size. So I apologize if that part wasn't clear. Based on your answers, I think some of you may not have understood where I was going with that. So effect size it's the proportion of variance accounted for the level 2 random intercept. That's what a main effect of a predictor is supposed to do. And then significance, this is a Wald test. So the estimate divided by the standard error is treated as a test statistic, either a t or a z, based on whether you're using denominator degrees of freedom. And then you can just use that directly as your test. That is valid if you are in REML or if you are in ML. You can do it always. And with respect to denominator degrees of freedom, a few of you mentioned that. Of the methods that are available, I think Satterthwaite or Kenward-Roger are considered the best ones with respect to small samples. It stops mattering real quick though, once you get enough level 1 and level 2 units. But I have Satterthwaite in all of my examples because that is available across all of the packages that I teach in, SPSS, SAS, R, and Stata. It is not available in M+, because M+ does not use denominator degrees of freedom, so everything in M+ is going to be a Z instead of a T. So, questions or comments on that question? Okay. So, main effects of level 2 time invariant predictors, their job is to adjust the intercept, therefore relevant effect size is how much intercept variance they accounted for. Then question 3, same idea but for a cross-level interaction. So a cross-level interaction is between a level 2 predictor that is time invariant and a level 1 predictor that is time variant. So a cross of the levels, so to speak, in the interaction term. And what do I need to do first before examining a cross-level interaction? Several of you got this right. What is my first step before fitting a cross-level interaction? We have one vote for test the random slope of the level 1 predictor. That's what I was going for. Several of you also mentioned make sure that you have the main effects of each variable in as fixed effects, and that is true. I did not think about that, but you are right about that too. So before you test a cross-level interaction between a level 2 time invariant predictor and a level 1 time varying predictor, you would have each of the fixed slopes for their main effects in the model, but more importantly, the random slope. Because the idea of a cross-level interaction is that it is supposed to be accounting for why the level 1 slope differs across level 2 units. So for the instance of time as a slope, for instance, why do people change differently? A cross-level interaction between time and some level 2 person characteristic would answer that question. Why do people change differently? And so if the random slope is in the model, then the relevant R-square would be that random slope variance that is accounted for by the cross-level interaction. If the random slope is not in the model, you run the risk of having type 1 error rates that are too high for the cross-level interaction, but the relevant R-square would then come out of the residual variance instead. So checking the random slope is important to make sure that that is the term to be accounted for by the cross-level interaction if present in your data. And the significance test works the same way. It's the Wald test that shows up next to the interaction term on your output, whether you're in ML or REML. Okay. Questions or comments on that one? Then last but not least, what if I want to talk about the significance and effect size for an overall contribution of a time invariant predictor. So if I want to talk about the role that it plays in the model, not just for its main effect, but as part of its interactions with other variables or cross-level interactions with level 1 variables. So how can I do a significance test for more than one slope at a time? I can think of two ways to do it. What do you think, though? How can I do a significance test of more than one slope at a time? Yeah, we got one vote for a multivariate wald test. So you can ask for the program to lump slopes together, and that will either spit out an f or a chi-square. So f times the number of slopes that you've tested equals your chi-square. The difference is whether or not you're using denominator degrees of freedom with the distribution. That is available via contrast in SAS, test in Stata, contest MD or GLHT in R. What about -2 log likelihood differences? Could I do a likelihood ratio test to answer the same question as to whether a set of slopes helps the model? I can under a certain condition and I can't under another. It depends. Yeah, it depends on my estimator. If I'm using REML, which is what we've used this entire semester because it gives us unbiased variance components in small level 2 samples, if I'm using REML, can I do a likelihood ratio test to answer questions about fixed effects? Nope. It's wrong. They're on different scales at that point because REML refers to the model residuals after the fixed effects have been taken into account. If I'm using ML as I would say, then can I do a likelihood ratio test? Yes, I could. So those are supposed to be asymptotically equivalent ways of answering the same question. If you're using maximum likelihood, you can do a wald test or you can do a likelihood ratio test. There's a third one called a score test. If they ever differ, I think likelihood ratio test is supposed to be the more valid relative to wald, but in REML, you can't do it that way, which is why I'm showing you the how to get an F that lumps multiple slopes together if that is an answer to your question. Is the transcription getting REML right yet, or is it still Rambo? Can anyone report? Still Rambo? REML is Rambo? Remo. Okay, it's Remo. I think that's progress. How about ML? What's ML? It is ML? If I say ML, I bet it is, but if it's ML, there's probably an E in there, I would think. Well, just so you know that Remo is Remol in papers. All right. And effect size. If I want to talk about the effect of a predictor sort of as a whole combined across multiple slopes, how could I do that? I could do it by reporting separate pseudo R-squares for each of the variance components, or I could do something else. What's that something else? Total, yeah, total R-square. So there are versions of that in the Wrights and Sturba suite as well. The idea being that you lump together all of the variance components again so that you can talk about the marginal variance of y and how much the predictor is responsible for. So they're complementary to talking about how well the model did with respect to each variance component in addition to how well it does overall. So, all right, any questions or any of that you want to talk more about?
I have kind of an overall question.
Please.
So I'm looking, for example, at like from the I think it was a review lecture 7B page 21. It just is like an example of a level 1 and then with the time invariant predictors at level 2. And like that made sense to me. And then doing this homework, I think I got confused about like putting like a predictor at level 1 and level 2, and in this example, education and group are at level 2, and time is at level 1. And I know, is it, could you maybe go through something like that and explain like why it's being included at one level but not the other one, or maybe an example of it, like a cross level of like a predictor that would be a cross level?
Yes, I can. Let me think of.
I don't know that I'm asking for the right thing, so if, if you have a different idea, sounds great.
Me. So an example that would be across levels, like where it's on both levels at once. Okay, yes, I can. Although it's probably going to take a few minutes to pull up. So this is the advanced MLM class where we did time varying predictors. Let's go to this one. So this is lecture 3. I'm pulling up out of that class. So while this is spinning, I can answer the first half of the question. I want this. Make it a little bit smaller. Open in Acrobat. Yes, let's do that, please. The web page is very hard. The reason that time in our examples is only at level 1 is because it only contains level 1 variance. So, and that is a consequence of having a time that is balanced across people and there's no missing data. So everybody has the same 6 occasions. There is no between person variation in time as a variable, and so it can't go into the level 2 model. Likewise, a time invariant predictor has no within person variation. It is a constant across the rows for the same person. So it can't go into the level 1 model because it doesn't have any level 1 variation. The outcome, though, has variation at both levels, right? That's the whole reason we have this multi-level model where we have within person level 1 information and we have between person level 2 information, and most time varying predictors operate the same way. So if you have, for instance, if I have a variable like stress measured daily across, this is like an EMA kind of study, ecological momentary assessment. Some people are going to report that they have more stress in their lives than others. Like they will have a higher mean stress score across the days of their observations. And simultaneously, some days are going to be worse than others. So to the extent, for instance, that I'm picturing stress as a predictor, if I've measured it repeatedly, it's going to have between person level 2 variation and within person level 1 variation in the same way that the outcome would. So I have to put it into the model in both places. My preferred way of doing this, skipping a little bit here, is to create 2 versions of the predictor that literally separate out its sources of variance into 2 distinct orthogonal predictors. So this is a technique that's called person mean centering in this context, where I would take the mean of the time varying predictor, so that's x bar right here, minus some constant so that it 0 is meaningful. And then the new level 1 predictor would be the time varying predictor, so xti is the time varying predictor here, and then subtract the person's mean. And then these 2 new variables, this PMX, which stands for person mean x, and the purple one within person x, which stands for or WPX, then between person is captured by PMX and within person is captured by within person X, and it looks like this when you put it back together again. So you can't literally put the same variable in both places, but you carve up its variance into its respective piles and you put those observed representations of that variance in respective piles. That is the way that you can do it if you have a using observed predictors only. But An alternative way of doing that is to treat your predictor as if it is an outcome and let the model estimate its random intercept variance and its residual variance in the same way that it does for the outcome. And so that is a multivariate approach. It's also known as latent centering instead, and that is better in most cases, but not all. So it's a very good question, like how do you know where it goes? In general, a predictor goes into the model, some version of it, I should say, goes into the model at each level at which it contains variability. So the examples that we did in our class this semester were constrained to variables that were purely level 1 for time versus purely level 2 for time invariant, but time varying predictors are going to be both.
That helps a lot, thanks.
Sure. So yes, you have at all the other material for that. Okay, other questions? So we were in, then if not, we were in example 7b around page 15-ish. We ended class with full saturation, as I recall, with a model with three-way interaction terms in it. So this one, I think if we have time, we can come back to that. But if it's okay with you, I would rather jump ahead to the polynomial models because that's what your homework's over. Does that sound fair? Yeah, good. Okay. So in your homework, there are 3 sections. Section 1 is just an unconditional random quadratic change model. It is the same model you ended up with in homework 3. So you can port your code over and use that as a starting point, although the data are different for homework 5 because I added a couple of variables. So that is going to be the starting point then for this set of examples is the same place, the unconditional random quadratic model. Okay, so I'm going to start then on page 18. So there's this handout had piecewise models of change and adding predictors, and now we're starting over using a polynomial model instead of piecewise. So linear and quadratic change. So we have session -1 is our time variable, so that time 0 is the reference for the model, which is at session 1. And I have a linear effect and a quadratic effect, and each of those effects has a fixed part and a random part. So everybody gets their own intercept, their own instantaneous linear rate of change at time 0, and their own rate of acceleration or deceleration, half of which is given by the quadratic coefficient itself. So then the fixed effect predicted outcome y hat here is just a function of the fixed intercept, the fixed linear slope for time, and the fixed quadratic slope for time. And those are the 3 terms that go into the model right there. They also go into the model right here. And just as a reminder, there are 2 versions of time in the SAS code and in the other program's code. Session is the ID variable. So session and time are different variables because they serve different purposes. Time 1 is session -1, which is being treated as a quantitative predictor. Time 1 has fixed effects in the model line and random slopes right here. And the only difference in the Stata code is that in specifying a random effect of quadratic time, I couldn't get it to take it as an interaction term. I had to make a new variable that was literally time squared. So it may be possible that I screwed up the code and that there is a way to make it work, but this is the way that I got it to work by brute force of making the squared version. And so then the R code, a squared term in R looks like this. Let me blow that up a little bit. It's I, and then in parentheses, the variable that you want squared with a caret and a 2. So I did that as a fixed quadratic effect in the formula here, and as a random quadratic effect of time within the second section here that gives the random effects. Okay, so any questions on the setup here? We're still predicting change in response time across 6 balanced occasions in a sample of older adults. Okay. So then here is the G correlation matrix. That's one of the pieces of information that I asked for in addition to just what shows up by default. One thing I want to note is this right here. Because of the way that I centered time, such that the intercept is at session 1 at the beginning, the linear and quadratic random slopes are very highly correlated. So this can cause a little more uncertainty than usual in terms of what the pseudo R-squares are going to be, because these things are so highly related to each other. So this is something to keep an eye on and potentially change your centering strategy if it goes to 1 and stays there, because then it will throw an error message that your G matrix is non-positive definite, meaning that there's something that's out of bounds here. So this is very close to that, but not quite. But otherwise, we have the variance components of the model. So the UN1122, that stuff, that refers to the random effects, variances, and covariances in the G matrix. So anytime that you see the same number in both places, like UN11, nope, not that one, UN11, UN22, and UN33, that means it is on the diagonal of the matrix. That's a variance. And it goes in the order in which you listed them. So if you list intercept first, that's going to be 1, 1. The terms that are left over are the covariances among the random effects. So in SAS, it gives me covariances and variances. I can then ask for correlations as a separate piece of output. Stata does the same thing. And in R, what you get depends on what package. So if you use, If you use NLME, which has LME, you get standard deviations instead of variances, and I believe you get correlations. If you use Elmer, you get variances and I think correlations. So just keep an eye on the output as to what you actually have, because it does vary across programs how they represent the model for the variance. But the point of the story here is that these numbers are our new baseline for predicting individual differences. At this point, each person has their own random intercept, linear slope, and quadratic time slope, and all the reasons why people differ from each other are characterized in this model. So this is our jumping off point for estimating R-square, because we want to see to what extent our time invariant predictors are going to make each of those go down. And then residual variance at level 1. Why are you off your line today? In this example, should not change, because characteristics that are constant, level 2 time invariant predictors, should not by themselves predict level 1 variance. The only way that they can is if they're part of a cross-level interaction with a level 1 slope that's not random, which is not going to happen in this example or in your homework. Okay, so then the growth curve right here, I have the labels. I got a question in my earlier class. I tried to find these labels that you put on here, and I couldn't get SAS to print them for me. Yeah, no. This is me being nice. If SAS actually printed what shit meant, I would not have a job. So this is job security for me, and hopefully for all of you. You learn how to crack the code to understand this output, and someone will pay you for that privilege so that they don't have to. But I have done this for you to remind you what each of these fixed effects means in here. So the intercept is the predicted outcome when your predictors are 0. In this context, this is going to be when time is 0, which is at session 1. Because of the quadratic, this linear time slope is the instantaneous rate of change at time 0. So minus 120 at session 1 is how much people are improving in response time per session. And then the quadratic operates on the linear slope, in this case by making it less negative as time goes on. So twice the quadratic, cough cough homework question, is how the linear slope changes per unit time. What you are given directly is half the rate of acceleration, so you have to multiply it by 2 to get it to the full rate. And this piece of output right here is the result of asking SAS to create a column of predicted outcomes and then correlating that column of predicted outcomes with the real ones. That correlation was estimated as 0.19. If I square that correlation, it works out to be about 0.04. So that is telling me that 4% of all of the variance in response time has been accounted for by the linear and quadratic fixed time slopes. So that's my baseline to judge against adding further fixed effects. Okay, questions on any of that for the baseline model? So that's section 1 of your homework. Now on to section 2. We have age as a time invariant predictor. So I know that sounds kind of like I'm saying the same thing twice, but I have two different variables here. I have age and I have time. In this study, keep in mind that people are not aging. This is during a 2-week period in which they're having these 6 sessions. So time is a marker of how many exposures to this task they've had. Age is their chronological age at baseline. So we're looking at whether or not older people improve more or less than younger people. And these are all older adults, but they're young old versus old, and that is the way they talk about it. So I'm including age as a time invariant predictor in each of my level 2 equations. So the main effective age gamma O1 here is going to tell me how age affects the intercept. Because age is included as an interaction with linear and quadratic time, I know that that effect on the intercept is specific to time 0, and the linear and quadratic time slopes are moderated by age as well. So then the equation for how you would get the linear time slope at any occasion for any age is right here. So it starts with this. The linear time slope at a minimum is the fixed effect of linear time. Then the model moderates it as a function of the terms that contain interactions with time. So I have T here as an abbreviation for session -1. So the first moderator is twice the quadratic coefficient. Typo. That should be 2O. I just changed that. I'll fix it after class, but I had put a copy and paste error. So gamma 2O is the quadratic coefficient. That's what should be there. Then we have this middle term right here, age multiplying the linear slope. So the cross-level interaction between age and the linear slope as a function of age. And then we have this one, which is the cross-level interaction of age by quadratic time, which still gets multiplied by 2. So it's a little tricky, but these are the ingredients that would allow you to write an estimate statement or a LINCOM statement or a contest 1D statement to get the linear time slope at any occasion conditional on any age. Quadratic time slope is a little easier. It's just a function of whatever the quadratic time slope is as a fixed effect, and then the cross-level interaction of it with age. And then if I go the other way, rather than talking about how age moderates rate of change, I can talk about how the effect of age changes across sessions. And this model predicts that it changes quadratically across sessions. So I can unpack that by filling in a value for time for each session to see what the instantaneous effective age would be at each session. Okay. Questions on any of that? So then the code. So I'm adding in these 3 interaction terms to the model. Actually, 1 main effect and 2 interaction terms. So this term right here with age just floating by itself, that's what I call the main effective age, meaning just the fixed slope of age. Because it's part of these interactions, this will become the fixed slope of age at session 1. Here's an example of how I would do a multivariate wald test to lump together the 3 age slopes to be able to talk about the joint combination of how age contributes to the prediction of response time. And here are some examples of how I would do a simple linear time slope or an instantaneous linear time slope at particular sessions for particular ages. So this is using the ingredients that were given on the previous page as to what the values are going to be. So at session 1, at a minimum, I need this. So when you're writing these statements, the first thing to write is the thing you're trying to estimate. What am I trying to get? I'm trying to get the linear slope. Okay, put that in there, give it a 1. Then what else you need is conditional on who it is the linear time slope for and at what occasion. So because it's at session 1, the quadratic term goes to 0 because I'm filling in time 0 for that. Time 0 times 2. Whereas at session 3, that's when time equals 2. And so it is 2 times 2 goes here. At session 5, that is time equals 4. So what goes here is an 8. So twice the quadratic coefficient. Okay, with me so far? So one thing to note in here is that even though I'm asking for predicted ages, I don't have age by itself. The only terms that go here have to have time 1 as part of them. So scan through your model, find all of the terms that have time 1 in them, and they go in here. So for age 74, I am filling in a -6 for age 80. Age is centered at 80, so if I want it for age 74, I fill in a -6. So this term stays constant throughout the 3 lines because this term only reflects how the linear slope is moderated by age. So I need to know the value of the moderator for age. From there, what goes into the last one is a straight multiplication of what you put previously. So this is -24 here because 4 times -6 is -24. Likewise, 8 times -6 is -48. The 3 middle ones here for age 80, because age is zeroed out, the higher order interaction is zeroed out. And then for age 86, it's the opposite pattern just with no minus signs. Okay, so stare at that for a second. Let me know if that needs more explanation or if you feel reasonably good about that. While I drink my water. I've hit my ration of caffeine for the day. Currently good about it. That's all I can ask for. There was, interestingly, I'm talking about interactions in my earlier class too, except they're not in longitudinal models, they're just in general linear models. And one of the students asked if it was a problem that they still had to look back at their notes to figure this stuff out and that they didn't have it like memorized yet. So in case anyone here is feeling badly that this doesn't just roll off the top of your tongue yet, no, it does not. Do you know how I made sure that this was correct, by the way? Because I actually doubted myself in putting it together. I'm like, do I put it times 2 or do I not put it times 2? I recentered my model so that I had age 74 like as a reference point and checked it. So I recentered it at different occasions and at different ages, and I made sure that these simple slopes that came out of the model then matched what my estimate statements were doing. So when you don't have green boxes to rely on, you can use tricks like that to make sure that you know what you're doing. Because this stuff is hard. It is. It does get easier with practice, but it isn't something that will necessarily just be super easy at any point. This term, though, is relatively easier because I'm estimating what the quadratic slope would be for different aged people. So then the same rule applies. Find all of the terms that have the quadratic slope and put them in here. Only terms that have the quadratic slope go in here, though. And because the quadratic slope is the thing I'm trying to estimate, that gets a 1. Then the value that goes with the interaction with age is the value of age for which you want the quadratic time slope. So the first row gives it to me for age 74. The second row gives it to me for age 80, which is what the model would give me directly. And then the last row gives it to me for 86. Okay. Is that much okay? Okay, see a couple nods. See some thumbs, that's good. So in thinking about the output, I think the most natural way to talk about these sorts of moderation models is how age changes the growth curve. Like that, I think, is an easier way to conceptualize it. But some research questions are phrased the other way. So in this case, we can spin it and look at what the model says how the age slope would change across sessions. And that is a more complex story. So to look at it that way, I have the effective age at each session, because here's my effective age at a minimum, and then it is moderated by time and time squared. So in this context, what goes into the coefficients is the value of time at which you want the age slope and time squared. So when you're estimating the effect of the time invariant predictor at each occasion, it's time and time squared. In this model, because of the three-way interaction here, I can also estimate simple, age by linear interaction terms. And here, if that's the thing I want, it gets a 1, and then it's twice the value of time. So I have my notes up here in the comments as to what goes in as the values. If you're estimating something about a linear slope, you give the quadratic slope time times 2. Otherwise, it's just time squared, like it would seem like it should be. So this gets a little ugly, but it's a consequence of the way that the effective age is changing over time. The first term describes how it is changing over time at session 1, and then the quadratic takes it and changes it further. So it's a complex, but I wanted to show you how I would go about talking about what happens. And once we have some numbers on it, it will probably make a little more sense. So then the same ideas show up in the Lincom statements in Stata. Note that for some of these you can cheat and use the dydx command to shortcut all of the Lincom statements for simple slopes. And in R, all of this shows up with these series of numbers here. So in the order in which it shows up in the equation, that's the key. So make sure that what you write up here is what it's actually doing, otherwise the order of these will be off. There. Okay. Any questions on the code or the setup before we look at the answers, the results? And don't worry, in your homework, I'm not going to ask you for 37 estimate statements. Okay, this is for demonstration purposes. I'm going to ask you for maybe 2 of these. So when you go typing your code, get the model right. Answer as many things as you can from your output, and then if you see a question that you can't answer with your output, then write some extra code to answer that question. How's that sound? So generally speaking, any estimates that are specific to the centering point of time are going to show up on your output already. So I ask you, if I tell you to center time 0 so that it's at the beginning, if I ask you any questions about something at the beginning, that's in your output. Likewise, if I ask you any questions about the reference point of the predictor, that's in your output too. It's only when you move off of the reference for what 0 is that estimate statements are required. So let's see what happened. Okay, just this much so far. Let me make it a little bigger. So these 3 terms right here, those were in my unconditional model. Because each of those terms now interacts with age, you can think of this effective age right here conceptually as this. As to what each term is supposed to be doing. The main effective age is the effect on the intercept. Time 1 by age is the effective age on the linear time slope, and time squared by age is the effective age on the quadratic time slope. So this is the reference growth curve for somebody who is 80. And then each of the 3 terms moderates the 3 aspects that create that curve. So if we start with this and this, the model is centered such that time 0 is the first occasion. So at the first occasion, an 80-year-old person is expected to take 1950 milliseconds to do this task. For every year older you are when you walk in the door, your predicted response time at session 1 increases or is higher significantly by 29 milliseconds. So predicted response time on the y-axis is shifted up or down by this main effective age, the effective age on the intercept, about 29 milliseconds a year slower for every year older. Okay, with me so far? Now this one and this one. Because of the quadratic terms, that time 1 slope is the rate of change at the first occasion. So I still have my prop here, telescoping thing here. We have a quadratic model, which means the rate of change starts here and it slows down over time. So we've got this side of the U happening. So at this point, the rate of change for an 80-year-old is negative 121 milliseconds a session. In older people, what happens to it? Yeah, I'll take gestures. Yeah, steeper, more negative, stronger, steeper, more negative. Any of those words work. Yeah, this minus 121 becomes more negative by 5 milliseconds per year of age. And it is maybe approaching significance. Can we call it that today? 0.09. That's my favorite euphemism, approaching, because it makes it sound like if you come back later, it'll be significant, like a cake or something. It's just not done yet. It's still baking. But no, not by conventional levels of significance. I talk about these things because I want you to know what to do with the coefficients. I know you know how to interpret a p-value. So yeah, it's not significant, whatever. I want you to know the direction. So what this is saying is that at the beginning of the growth curve here, older people start out higher meaning they're slower, but they change more quickly. So they have more room for improvement, and initially it looks like they are improving more as a consequence. Okay. Good with that? Now the quadratic. What the quadratic is doing is slowing the curve down. So the rate of change in response time is diminishing as time goes on. More practice stops helping as much. So the half the rate of, let's call this deceleration, is about 14 in an 80-year-old. That quadratic coefficient becomes, which is this, as age increases, what happens to it? More positive, less positive, more negative, less negative. Yeah, this is a more positive. So the quadratic coefficient is stronger in older people. Non-significantly, but whatever. Yeah, so more deceleration, that's a good way to put it. The curve is slowing down more if they're older. So it starts out higher, starts out steeper, but slows down more. And I do have pictures, by the way, because this is the point where your reader's going to be like, what? And you show a picture. I don't know if I have it for this model, but I have one for another model. So older adults start out slower, initially change faster, but that rate of change decelerates more. And so then I can estimate all these sort of specific slopes to zero down into that story. Okay, what would it look like for age 74? What would it look like for age 80? So start out higher, slow down more, decelerate more. Okay. With me so far? Now, the other way of talking about it is what happens to differences between people of different ages. Does age matter more at the beginning of the study than it does at the end? So if we flip this on its head, start with this one and talk about what happens to that coefficient. 29 is the slope of age at session 1. For every year older you are at session 1, you're slower by 29 milliseconds. What happens to that slope as time goes on? This is the tricky part. At the beginning, the slope is weaker. So at session 1, this first interaction term starts kicking in, and for every additional session, that age slope is less positive by 5. But then that decrease in the slope of age is diminished as time goes on. And that is a mouthful, at which point you have to say, yeah, I need a picture for that. So the effective age is predicted to change over time in this complex pattern that's given by these two terms that work together. So it looks like the effective age is diminishing over time, but to a lesser extent as time goes on, is the way I would phrase that. So I can get what the model says the effective time, or excuse me, the effective age would be at any session to help explain that. So if you look at the change in this coefficient across sessions, the slope of age is 29 milliseconds a year at the beginning. By session 2, it's down to 24. By session 3, it's down to 20. Then it goes down to 18, 17, 17. So the way that the slope of age is changing is quadratic across sessions as a consequence of this model. All right, and then here's the other ones too. which are harder to interpret but complete the story. I think we've got all the questions on the fixed effects. Okay. So those are the patterns. These coefficients, though, are in units. So 29, for instance, is per year of age change in response time. I can tell from the output whether or not that's significant, but significance is always a function of sample size as well as effect size. So I need to supplement this with some kind of assessment of effect size. There's various ways that I could do that. I could take this t-test statistic and turn it into an r or a d. I could also do pseudo r-square. So I have total r-square first. It looks like the correlation between the response time outcome predicted by time and age with the original outcome is 0.33. The square of that is this. So we've picked up another 7% of the variance or so by adding in these three effects of age. That's an overall estimate of the effect of age. We can also look at how age has changed each of the variance components. So UN11 went down about 10%. UN11 is my random intercept variance. So which of my three terms is responsible for that 10% decrease? Age by itself, age by time, or age by time squared? Got one vote for age by itself. That is correct. So the main effect, so to speak, age by itself, adjusts the intercept. As a consequence, the intercept variance has been reduced by 10%. 10% of all the reasons why some people started out slower than others is because of their chronological age. 90% of the reasons we don't know yet. Likewise, this one right here, 2, the second term that we put into the random line is time. It went down about 3%. Which term did that? You got two choices. Age by time. So age by time was the one that was marginally significant-ish, reduced the linear time slope variance by 3%. That means the last one here, this is quadratic time slope variance, age by time squared. Reduce that one less than 1%. By the way, if anyone is scribbling what I'm saying furiously down, stop it. Do you know why? Because words. The last 2 pages of the handout is a result section of everything I'm saying. So, no scribbling needed. All of the other result sections are already in the textbook, which is why I haven't had them up to this point for the most part. But everything I'm saying is in there, so no worries. Let me find where I was here. Nope, too far. Okay. Well, while I find where I am, let me ask, are there questions? Scrolling, scrolling, scrolling. Nope, still in piecewise models. This is what happens when you have a 36-page handout. I did it to myself, I know. I have no one else to blame but me. So that's the kind of thing you get to do in section 2. And then there is one more, which is asking you to add the effective group, section 3. And in this example, for your homework, group is binary. So just dummy code it and leave it in as a quantitative predictor. I would not recommend using it as a factor variable because that's not going to map onto what the code's supposed to look like. Here we are. I found where I was. Age and reasoning. So even though this example has quantitative predictors, conceptually there's nothing different if you use a binary predictor for group as a moderator at level 2. It would just have values of 0 or 1. So that's what I would recommend. So then I'm leaving age in the model, and I'm adding a second level 2 predictor in this example for reasoning. So yours would be group instead, but it's very much the same. And then I have all of the ingredients for how the model tells you what the linear effective time should be at any occasion and for any person. And this is still wrong. It should be 2:0 for that one. And quadratic time for any age and any reasoning. Age at any occasion and reasoning at any occasion as well. So the exact same ideas as before. You go into the fixed effects, you pull out the terms that have that, whatever you're trying to estimate, factor it out, and then what's left is how the model tells you what the simple slope should be. So then all of the code looks pretty much the same. I had demonstrating reasoning for different levels of reasoning, ±5 as ±1 standard deviation. And all of that is pretty much the same. And we can look at the output before we adjourn. So now this is my reference growth curve for somebody who is not only age 80, but also reasoning 22, which was near the mean of this variable. These three terms still talk about how age moderates each aspect of the growth curve. Same pattern as before. Older people start out slower. They change more initially, but they decelerate more as well. For this one, what does that one tell me? Main effective reasoning. It is -27 as a coefficient, and it is significant. What's that telling me? What do main effects do of the time invariant predictors? Yeah, RT drops with deer IQ. Decreased. There we go. It's like if that's a shorthand, I'm not privy to it. Yeah. So in smarter people, response time is lower. In less smart people, response time is higher. At the beginning. So RT at session 1 is what's being moderated here. Smarter people also decrease more initially and decelerate more as well. So it's the same pattern. And I think I have a picture of this one, if memory serves. Yeah, I do. I knew I had a picture, but it just wasn't age, it was reasoning. This is what it looks like. So the code that I used to make this is in Excel. I did that for pedagogical purposes, but you could also output predicted values for prototypical people. So this plot shows time on the x-axis. Stop that. There we go. For different kinds of people. I'm trying to get it all on the screen here, and it's not letting me. So reasoning 17 is the top line. So these are the less smart people. They start out higher. They have a steeper rate of change initially, but they decelerate less. People who are smarter start out lower, they have a steeper rate of change. That's how it was, and they decelerate more. So if we look at the differences of these slopes, that's how reasoning moderates the growth curve. The other way to think about it is how the vertical differences between these lines change over time. So people are closer together at the end than they are at the beginning. That's the other way to think about reasoning by time squared. All right. See, pictures. Pictures make it better, right? Pictures make it better. Pictures always. All right, have we hit saturation? It's 312, so I'm guessing we have. Yes, saturation hit. All right, any last minute questions before we say goodbye for today then? Nope, and if you are, you can come hang out with me in office hours. So, all right then, it is Tuesday, which means I do not say have a good weekend. I say, see you Thursday. Let me know if you need anything. Thanks for coming. Hang in there.